Hi guys, welcome to our channel DSP NIT AP. This is Jyothsna from the ECE department. In this lecture, let us understand one of the most important properties of discrete Fourier transform, that is circular frequency shift property. The circular frequency shift property states that if a discrete time signal when multiplied with an exponential term e to the power plus j2 pi ln upon capital N, then we can observe that its discrete Fourier transform will be circularly shifted by L units, where L is the frequency index, N is the time index, capital N is the number of samples in the frequency domain. Let's check the statement. Discrete Fourier transform of x of n is capital X of k. Then the discrete Fourier transform of x of n multiplied by e to the power plus j 2 pi ln upon capital N is x of n minus L modulo capital N. This is the statement and mathematical expression. Here we have two ways to prove the statement. Then what are we waiting for? Let's check them out. So if we check the statement again, it says that the multiplication of the sequence by the Twiddle factor or the inverse Twiddle factor is equivalent to the circular shift of DFT in time domain by L samples. Wait. Before we get into the proof, what exactly is this Twiddle factor and the circular shift? Let's check them out. First, let's check the shifting of the sequence. There are two ways in which we can shift a sequence from n is equal to 0 to n is equal to 1. Circular shift and linear shift. First, the circular shift. In this, the frequency is circularly shifted. That is, the DFT is being multiplied with a complex exponential. And the other type is the linear shift. In this, the sequence gets shifted linearly and there is no need of multiplication with the exponential term. What exactly is circular shift? Let us assume an endpoint signal x of n, where n can be any whole number, and the signal g of n is equal to x of n minus m modulo capital N represents the circular shift of x of n by m samples to the right. For example, if we take g of n is equal to x of n minus modulo n and substitute n values from 0 to capital N minus 1 modulo capital N and substitute the values from n is equal to 0 to capital N minus 1, then we will get 0, g of 1 and g of 2, and we must repeat this process upon g of capital N minus 1. Hence, we'll get x of n minus 2 modulo n is equal to x of n minus 2. Seems to be so heavy, right? So now let's take a small example, that is, let us assume x of n is a 4-point signal and its sequence is 1, 3, 5 and 2. Upon circular shift by 1 unit, we will get x of n minus 1 modulo capital N is equal to 2, 1, 3, 5. We did nothing, we just shifted the sequence rightwards by 1 unit, and hence we got 2, 1, 3 and 5. This is circular shift. As we came to know what a circular shift is, let's have a look at what the Twiddle factor is. Twiddle factors. Twiddle factors are the set of values that can be used to speed up the discrete Fourier transform and inverse discrete Fourier transform. It can also be represented with the letter capital W. For a discrete sequence x of n, we can calculate its discrete Fourier transform and inverse discrete Fourier transform using the following equations. Discrete Fourier transform equation is x of k is equal to summation n is equal to 0 to capital N minus 1 x of n multiplied by e to the power minus j 2 pi n k upon capital N, and inverse discrete Fourier transform equation is x of n is equal to 1 upon capital N summation n is equal to 0 to capital N minus 1 x of k multiplied by e to the power plus j 2 pi n k upon capital N. Now we came to know what circular shift and Twiddle factor means. Let's check the method 1, that is LHS to RHS, and prove it. Let us assume xp of n be a periodic discrete time signal and xd of k be its discrete Fourier transform. Later, when this xd of k is being multiplied with the exponential term e to the power minus j 2 pi kl upon capital N and applying the inverse discrete Fourier transform for the same, we get 1 upon capital N summation k is equal to 0 to capital N minus 1 e to the power minus j 2 pi kl upon capital N xd of k multiplied by e to the power plus j 2 pi kn upon capital N. Now from this, let's group all the exponential terms together and write it as 1 upon capital N summation k is equal to 0 to capital N minus 1 e to the power j 2 pi k into n minus L modulo n multiplied by xd of k. This looks exactly like the inverse discrete Fourier transform evaluated at n minus L, that is, it is the shifted version of the periodic action, and hence we can write it as xp of n minus L. If we apply modulo to the same, we get x of n minus L modulo n, which is the RHS part. Hence, we proved LHS is equal to RHS, and hence we are done with the proof using the first method. Let's move on to the second method, that is RHS to LHS. Let's prove it. We start by taking the RHS part, that is x of n minus L modulo capital N, and apply discrete Fourier transform for the same. Then we get summation n is equal to 0 to capital N minus 1 x of n minus L modulo capital N multiplied by e to the power minus j 2 pi k n upon capital N. Now we will split the limits from 0 to n minus 1 as 0 to L minus 1 and L to n minus 1. Then we get summation n is equal to 0 to L minus 1 x of n minus L modulo capital N multiplied by e to the power minus j 2 pi k n upon capital N plus summation n is equal to L to capital N minus 1 x of n minus L multiplied by e to the power minus j 2 pi k n upon capital N. Here in the second term, since n is greater than or equal to L, so we don't need to use this mod operation, and hence in the first term also we need to remove this mod, hence we must use the explicit form to remove this mod function. That is, replace n minus L with capital N minus m plus small n, and hence we can write it as summation n is equal to 0 to L minus 1 x of capital N minus L plus n multiplied by e to the power minus j 2 pi k n upon capital N plus summation n is equal to L to capital N minus 1 x of n minus L multiplied by e to the power minus j 2 pi k n upon capital N. This expression seems to be bulky, so we introduce a variable m whose value capital N minus L plus small n. We get summation capital N minus L to capital N minus 1 x of m in e power minus j 2 pi k into m plus L upon capital N plus summation m is equal to 0 to n minus 1 minus L x of m e to the power minus j 2 pi k into m plus L upon capital N. It's time to combine all the terms into a single sum and take out the common exponential term, that is e to the power minus j 2 pi k L upon capital N, and hence we get the following expression, that is e to the power minus j 2 pi k L upon capital N into summation m is equal to 0 to capital N minus 1 x of m into e to the power minus j 2 pi k m upon capital N. After simplifying this, we will get the following result, that is e to the power minus j 2 pi k L upon capital N multiplied by xd of k, which is our final result, that is the RHS part. And with this we proved the statement using both the methods, and we have reached the end of the video. Thanks for watching. Please do like, share and subscribe to our channel and hit the bell icon. Thank you.